next speaker. It's Jacopo Emmenegger, and we talk about elementary fibrations and questions of groupoids.
Thank you. It's very nice to be here in this very pleasant meeting, and well, I would like to thank the organizers for inviting me to give this talk. Also, I have to say that I'm not sitting because I'm lazy or maybe I am, but that's not the reason I'm sitting. It's just not in my best shape. Anyways, let's get to the talk. I will start more or less where Pino left you. In the theory of doctrines, there is this diagram that relates primary doctrines, elementary doctrines, and elementary doctrines with quotients. That basically says that everything is either comonadic or monadic over the previous categories. So the straight arrows are like forgetful functors together with their adjoints, and these comparisons are equivalencies. So basically, both elementary doctrines and doctrine with quotients can be recovered just from a single two comonad, a collapse idempotent comonad on primary doctrines. And this was realized through a series of steps, which are basically these papers. So first, it was a result by Maietti and Zolini that there is this junction, and the left adjoint is actually the functor that appeared in the last slides of Pino Stoll. So it's the functor that takes a doctrine to the doctrines of descent data on equivalence relations of the original doctrine. And then Fabio Pasquali realized that to build this functor, you don't need actually to have an elementary fibration. You don't need equality. Conjunctions are enough. And in this way, you get a right adjoint this time to this other forgetful functor. And then Davide Trotta proved in his thesis that this canonical comparison is an equivalence, so that quotients are monadic over quality. And then finally, together with Fabio and Pino, we proved that also this comparison is an equivalence, somehow closing the picture. And now, the aim of my talk today is to lift this picture to the case of non-faithful doctrines, so growth-ending fibrations generally. All right, let's get started. So instead of elementary doctrines, we're going to deal with elementary fibrations. But I'm not taking the functorial definition, or the definition that uses left adjoints to reindexing, but rather I'm taking a perspective that I think was also shared by Thomas in his tutorial, and one could say that perhaps this perspective goes back to Benabou, where instead of speaking of reindexing and adjoints to this reindexing, we speak of the properties of the total category. So we only deal with arrows in the total category over arrows in the base category. And instead of reindexing, we have Cartesian arrows. And instead of left adjoints, we have co-Cartesian arrows. So a fibration is elementary if it has finite products, meaning that both categories have finite products and fibration preserves them. Which is the same thing as saying that the base has finite products and each fiber has them, and reindexing preserves them. And then instead of the left adjoints to reindexing along diagonals, we require the existence of co-Cartesian lifts. So co-Cartesian arrows have a dual universal property with respect to Cartesian arrows. So let's say that this is supposed to be co-Cartesian. So if you have a pair of arrows like this, and you have a corresponding triangle downstairs, where this is the diagonal in this case, And if you can close this triangle here, then you can close it also upstairs with a unique arrow which is on top.
What are those decorations? Co-Cartesian of the arrows? Let's understand the diagram. These
mean-
are co-Cartesians?
This one is co-Cartesian.
Okay. And the other decoration for the arrow?
And this one I'm getting there.
Okay.
This one is Cartesian.
Oh, all right. Let's understand the diagram.
Yeah. No, I'm going
sorry.
to explain this diagram in a second.
Maybe one more. So the vibration itself, the double arrow is not suggesting subjective or anything.
No, it's just saying that it's a vibration. It's a notation for a vibration. To distinguish it from a generic functor. Okay, yes, thanks. Okay, so then we have these co-Cartesian lifts, and then, of course, we need Beck-Shevali and Frobenius reciprocity, which in this framework are reformulated in this way. So, Beck-Shevali is something we call product stable. I mean, it's Beck-Shevali only with respect to this very special full-Beck squares involved in diagonals. And it says something that Thomas also mentioned in his tutorial. Whenever you have a co-Cartesian arrow leading over this diagonal, and you have Cartesian arrows here and here over an arrow of this form, then of course there is a unique arrow induced here by the universal property, and this arrow must be co-Cartesian as well in order for Beck-Shevali to hold. And then Frobenius reciprocity instead is formulated as saying that whenever you have a co-Cartesian arrow over a diagonal, if you pair it with a Cartesian arrow over the same diagonal, then you also get a co-Cartesian arrow. Okay, so this is the basic structure we're going to reproduce. In the first part of the talk, I will describe you the construction of a co-free elementary vibration that will correspond to this right adjoint here. Okay, so first few examples. So the first three you've already seen in Pino's talk. They are faithful elementary vibrations, so, elementary doctrines. The other three are non-faithful elementary vibrations. So the vibration fun over Z called when we have finite limits. Here we need a strict initial object because that's I mean, we need to be able to define the Kronecker delta. And then there is also this example where you take split isovibrations. It's important that you take split isovibrations and morphisms that preserve the cleavage on the nodes. If you take the full subcategory of split isovibrations, you get the vibration that is used by Hoffman strikers in the groupoid model, and that's not elementary. Okay, so let's have a better look at these co-Cartesian lifts, because the Beck-Shevali and Frobenius reciprocity allows us to basically reconstruct all the co-Cartesian lifts at any object A, starting just from those at the terminal object in the fiber. This is the terminal object in the fiber over X. So we have a co-Cartesian lift here. We can reindex it along this product projection. We get co-Cartesian arrow here by Beck-Shevali, and then we pair it with the Cartesian arrow over the diagonal, and we get a co-Cartesian arrow which must be isomorphic to the co-Cartesian lift that we know exists. So we obtain in particular these isomorphisms, and I mean, it's a simple fact that this fiber product is actually a pullback in the total category. It's not difficult to see. So we can assume that these co-Cartesian arrows are constructed in this way from these simpler co-Cartesian lifts at the terminal object in the fibers. And this is going to be very useful. Okay. So now let's have a better look at these guys here. So I'm going to write this Ix for the codomain of this special co-Cartesian lift at the terminal object. And using the universal properties of the co-Cartesian arrows, you can prove that this object here has the structure of a groupoid in the total category. And this groupoid lives over this co-discrete groupoid on X. And right, you have groupoid equations. Simply, I mean, you prove them by precomposing with delta X. I mean, you show that they hold on reflexivities, then they hold general. That's what co-Cartesian is telling us. I mean, something very familiar for people used to type theory. It's just that here everything is stricter than in conventional type theory. Okay, so we have a groupoid in an elementary fibration over every object X, from the product of X itself. We have a groupoid, which we understand as the groupoid of equality. I mean, this is no surprise that it's a groupoid, at least after Hoffman and Stryker's groupoid model, we know that equality can be evenly structured. Okay, so let's try to abstract this structure. And so we define a P groupoid, so a groupoid relative to this fibration P, to be a groupoid in the total category E over the terminal object on X, which is sitting over the co-discrete groupoid on X downstairs. And you have a category of groupoids. I mean, you define both these in the obvious ways. And you have a fibration of, I mean, this category is fibered over B by the object functor. Right, so the first example is trivial by definition, more or less. In the second case, if you have a category with pullbacks and you take the cot fibration, then groupoids in P are precisely internal groupoid C. And if you generalize slightly the setting, so instead of having products, I mean fiber products in E, you take that each fiber has a monoidal structure, you can like redefine the notion of groupoid relative to this monoidal structure instead of the Cartesian monoidal structure in the fiber. So in particular, this fund of a monoidal category will have this monoidal structure in the fiber. And in this case, you recover enriched groupoids, actually. I mean, this is also a framework. You can do it with categories, of course, instead of groupoids. It's a framework that somehow unifies the internal and enriched version of categories. This is not new. I mean, it was already observed by Mike Schulman, and also Nico Diorzi had some work on this. But they dealt with indexed categories instead of vibrations. And I don't know, I feel the vibrational framework is clearer, at least to me. Anyway, this is just to give you an idea of what you can do with this groupoids, besides for what we are going to do. Okay, and so now we have the corresponding notion of a P equivalence relation in the context of a non-faithful vibration. And now we want to understand what is set data. So they call these were the predicates in the doctrine which are invariant under the equivalence relation. And to express this notion, we speak of an action of a groupoid on the object A, which lives in the fiber over X. So action is given by an arrow of this form, which is leading over the second projection, such that these two diagrams commute. I mean, this should be pretty familiar. And in particular, if P is elementary, you can of course consider these equality groupoids. And in this case, every object in the fiber over X has exactly one action. I mean, this is saying that simply the equality is the minimal groupoid, or that everything is invariant under equality, depending on how you want to put it. Okay, so up to now everything is fine. But So basically, we want to construct a fibration where the object upstairs are these actions, and downstairs we have groupoids. But as you can expect, in the non-fatal case, the calculations can become quite cumbersome. So to do it by hand is quite painful. And also, I mean, you find yourself doing a lot of familiar things, actually, because I mean, it's clear that these things should be somehow algebras for some moment. They have the shape of an algebra. But notice that they're not vertical, because they're not over the identity. So if there is a monad, it's not going to be a fiber monad. So we need to find a monad that acts downstairs, and downstairs we are acting by product with X. And well, product with X is a co-monad, unfortunately. Well, maybe not so unfortunately, because we can recover a monad if we take the Kleisel category instead. I mean, you could take the coalgebras, but I will argue in a moment why you don't want to take coalgebras. Right, so the monad we want to take downstairs is this one. Notice indeed that its unit is this Kleisel arrow, which corresponds to the diagonal, and its multiplication is this arrow, which corresponds to, well, the arrow that we have below composition, the one that forgets the object in the middle. So this setting is it's very similar to what Urlo talked about, in the sense that we have a family of monads, here indexed over object of P. This is slightly more general in the sense that the domain of the monad is also varying according to the object X. But again, at least when doing things non-faithfully, I think that fibrations are way more convenient than indexed categories. So instead of dealing with indexed monads, I think it's more convenient to deal with fibered monad. So basically, it just amounts to collect all these guys into a single category. So here is the adjunction that you get. This is again a comonad on this category, which is taking a pair of objects and multiplying the first object with a second and then keeping track of the second object. And the Kleisel category of this comonad is the total category of the simple fibration on V. This is because the fibers is very well known. The fibers of the simple fibration over V are the Kleisel categories of the reader comonad. Right. So what happens if we take coalgebras instead? Well, coalgebras of the reader comonad are slice categories. And, well, unless P has finite limits, this is not a fibration. So that's why we don't want that. And by the way, I think this also, seems to suggest that the category of fibrations doesn't have the construction of coalgebras. Just a side remark. Okay, so now we know what is happening downstairs, and we want to understand how we can find a monad on the total category. Here is the construction. So let me walk you through this diagram step by step. So first, let's look at the front part of the diagram. So we have these 4 functors. This is the fibration. These two are given by the Kleisel adjunction. This is the simple fibration, and this is the left adjoint of the Kleisel adjunction. This is the vibration of objects of the groupoid vibration that we saw before. And we're taking the limits of this W diagram, which you can construct as a sequence of pullbacks, of course. You can also take the product of these two guys and take a single pullback. It's no big deal. And in this way, you can see that this functor is going to be a vibration because it's a pullback of a vibration, and this functor is going to be a vibration because it's a pullback of a vibration. we take this limit, so the objects are given by a groupoid, a pair of an object Z. Let me write it. So we have a groupoid, a pair of objects where the second is the object of objects of the groupoid, and then you have something in the fiber over the product Z times X. This is what the L is doing. It's taking this pair to the product. Okay, so this is the total category on which the upstairs monad will act. And how does it act? Well, it's just keeping the groupoid as it is. And then downstairs is acting as the monad on the classic category that we saw before. And then upstairs is doing, is doing the fiber product with the object of arrows of the groupoid. This was the domain of our actions, which we call. And by the universal property of the limit, we get this functor h, which is not just a functor, it's a morphism of vibrations together with m. And is something that leaves, you see, m is over b, is fiber over b, h is fiber over GPD. And so the morphism, the square itself, is fiber over this functor O. And using the groupoid structure on these guys, you can easily show that this pair, that the upper functor is a monad, and therefore the pair is a monad in the two category of vibrations, in the formal sense of street, over this vibration here. Right. So this is how we construct the monad, and then we can apply the construction of algebras, and we get this vibration, which is fibered over the vibration of objects of the groupoids. Which is all very nice. There's only one problem here, in that the algebras of M are a bit too general. I'm not sure if you ever dealt with this kind of functions. I will be interested to know, actually. So you see, these are functions from this product into the first component that does nothing if the two things are equal, and that basically composes somehow. I don't know how to say. I don't know if you've ever seen these things. I would be interested to know. But anyway, the point is that there are too many. We're not interested in all these algebras. Like this.
Why is this not an actual groupoid? Like, where's the extragenerality?
Is it's a co-discrete groupoid. But like what you do with that, like how they are used for, that would be interesting to know. Anyway, we're not interested in all these actions, but only in those that gives us the second projections, because the actions were over the second projection, and these are coming from very simple algebras of M. So those over the terminal object, very trivial actions. So what we do, we just take the pullback over the inclusion of these very trivial actions. And in this way, we recover the total category of actions, and then we consider this composite into the category of groupoids, and it turns out that this composite is a vibration itself, because actions are closed under indexing over these very trivial M actions. This is very straightforward to see. So this red vibration is going to be our co-free elementary vibration on P. So now we want to lift everything to, oh, well, first, I have some examples, right? So when P is faithful, we recover the doctrine that Tino presented in the last slides of this tutorial, which consists of the base are P equivalence relations, and in the total category or in fibers you have objects with exact data. Then you can look also at very trivial fibrations. You recover, for example, totals of G sets or continuous G actions according to the category you consider here. And remember that if we take the cold fibration, then GPD in groupoids in the fibrations are internal groupoid in C. And it turns out that the actions are precisely the internal actions that were considered by Janelitz and Tolan. Right. So actually, before going on with the construction of the two comonads, I would like to mention something else, because here we have that the actions are some algebras; they're not all algebras. So it'll be interesting to know in which cases they are all the algebras of a monad. And one answer is given when we consider an existential elementary doctrine. So now we also have these left adjoints. Now I'm departing a bit from my Benelux perspective. I hope you will apologize, forgive me for that. And anyway, the point is that if we consider the underlying functor of our upstairs monad, and we compose it with this left adjoint, then we also get a monad structure on this composite. And it turns out that algebras of this monad are precisely the actions of the groupoid X. So in an existential elementary doctrine, the actions are precisely the algebras of a monad. There is this monad here. And there is a bit more, because in an elementary fibration, I told you that we have a very simple groupoid, which is the equality groupoid. And in fact, you can also define another very natural groupoid, which is the kernel groupoid. So you pull back the equality along any arrow. In the code, this would be a kernel pair, the usual thing. But yeah, you can do it in general. So you have this kernel groupoid, and you also have, you can construct this functor, which in the faithful case is going to be a left adjoint along to reindexing along F, but in the general case it's not. Because we don't have enough factual conditions, basically. But you can still show that this guy is equal to this composite. So in particular, this is a monad as well. And it turns out that if the base has pullbacks and our fibration has now vector value for all pullbacks, then you can show that the actions are precisely the usual descent data for F, as they are defined with respect to the kernel pair now, not the kernel groupoid. These are the actions with respect to the kernel groupoid. So there is a mismatch between upstairs and because the kernel pair lives downstairs. So and to match the gap, to bridge the gap, you need vector value for all. But if you have this, these are hypotheses of the Benelux-Rubel theorem, and basically the Benelux-Rubel theorem then follows from this isomorphism and this isomorphism. This was something interesting to tell you. Okay, so this is something you can do with these groupoids and actions as well, not directly related to work. But so let's move on with the construction of our comonad. You can show that the function that I described before leads to a two-functor. And basically, in the first step, we start with a morphism of vibration. The limit on which this monad acts allows us to define a laximorphism of monads, which induces, by the formal theory of monads, a morphism of vibrations between the vibrations of algebras, and again, which restricts to the vibrations of actions. Then something similar happens for two cells, and then you can show that this two-functor has the structure of a co-lax idempotent comonad on the category of vibrations with finite products. The same thing that happened in the faithful case. And right, so this statement is just oh, maybe something I can tell you here also is that we first tried to do this in the indexed case. So when instead of a single monad for a fibration, we had a fiber monad, indexed monad indexed over groupoids. And I mean, in that case, these steps become quite unmanageable in the sense that already to show that a morphism of vibrations induces a morphism of a lax morphism of monads, you have to consider a cube where every side is filled with a two cell, and you need to whisker all these two cells and check if they're equal. And you have like 2 or 3 of these cubes. And when you move to 2 cells, then you need to stack these cubes, one on the top or side of the other, and as I said, it's quite painful. While in the fiber setting is very straightforward. I mean, as I said, you have a limit. The limit induces the action on arrows on 2 cells, formal theory of monads plus the rest of the job. Okay. So we have this two-functor with the structure of a collapse idempotent comonad. Oh, by the way, I didn't say it before. I'm not sure whether it was mentioned. I think Pino mentioned that, but let me recall it. Collapse idempotent basically means that if you have a coalgebra on some object, then the coalgebra structure is going to be essentially unique. So any other coalgebra structure will be canonical isomorphic to that, which is something you would expect from equality and quotients and products and all this kind of stuff. I mean, it's yeah. Okay, so the co-unit of this comonad is given by a pair of forgetful functors. So this is our old friend, the op vibration of objects of the groupoid, and this is just forgetting that there is an action in, right? And now a coalgebra is a section of this guy. So in particular, is mapping every object X to a groupoid on X, which is going to be the groupoid of equality for that object, and is mapping every object A in fiber over X to an algebra, to an action for this equality groupoid, ensuring that this object is going to be invariant under this groupoid equality. So in other words, a coalgebra precisely keeps the vibration B with the elementary structure. It's just a reformulation of the definition. In particular, this P bar has a coalgebra. I mean, it's co-free, right? So the co-multiplication is a coalgebra, and therefore you can conclude that this functor actually lands in the two category elementary vibrations. This is elementary because it has a coalgebra, the co-multiplication. And once you know this, well, it's easy to show that it gives actually oops, this should be right adjoint. Sorry for the typo. This is a right to adjoint to the forgetful functor. Otherwise, yeah, we wouldn't have a comonad. Sorry. Yeah, and it's actually very easy to show that the comparison to functor is an equivalence. Right, I think it's all I wanted to say about this slide. Okay, so let's get to the other side of the picture. So remember that we had the right-hand side of the diagram in the first slide that was involving doctrines with products and doctrines with equality, elementary doctrines. And now in the theory of doctrines, now why you might be wondering why the reason of the scare quotes. And the fact is that while we have a notion of a doctrine with quotients that was given by Maietti and Rosalini, as far as I know, I'm not aware of any definition of a fibration with quotients. But feel free to correct me and point me to something.
Von Jacob says one in the book. It's left.
Okay.
Oh, yeah.
But it's not, yeah. It's a different.
I mean, it takes the extension of the last. So
Yes.
Right. Okay, then maybe I should check whether we get the same. Yeah, anyway, so this is the two adjunction that we have here. Now the adjunction sign is in the right side, so this is the right adjoint. And this induces a two-monad on these two categories, which is going to be large-sided potent because the co-monad here was large-sided potent, just a consequence of this fact. And the underlying functor is still the same, exactly as in the Phaeton case. And in particular, this is also very standard. For an elementary fibration, the unit is just giving you the coalgebra structure on P. Or if you want, the coalgebra structure on P allows you to define the unit, depends on the slide you want to look at the thing. And now instead, an algebra for the monad that you have on elementary fibration is a pair of functors like this, such that this pair is a left adjoint to the unit with invertible co-unit. This follows from the theory of like-sided potent two monads, as in the paper by and the fact that we have this adjunction is very useful. So in particular, the fact that the co-unit is an iso is telling us, for example, that if you apply this Q to the equality groupoid of our elementary fibration, then basically you do nothing, which is something you would expect from a quotient of an equality relation. Right. So what we can do with this adjunction is the following: in that if you have an arrow between morphism of groupoids, so an arrow f from x to y, and this f bar is basically telling us that this arrow f is preserving the equality groupoid. The relation given by the groupoid. That's another way to see it. Then the downstairs part of the adjunction. So this functor here is mapping an object x to the groupoid, to the equality groupoid of x. Is the downstairs part of this unit. And the adjunction is telling us that the commutativity of this diagram, one commutativity implies the other. These squares are transpose one of the other. And you can define, because this is invertible, because that's a co-unit of the adjunction, we can define this arrow here, which is going to be our quotient arrow. And right, and the adjunction then is I mean, the bijection that you have between the two transposes is actually giving us a bijection between morphism of groupoids of this kind and arrows out of the quotient that that make this triangle commute. So this is also something you would expect from a quotient. And right, and these are very well-behaved quotients in the sense that you can show that the groupoid is the kernel groupoid of Q of this quotient map. And you can also show that all these arrows are of effective descent in the sense that the fiber over these quotients consists precisely of the actions of our groupoids. Okay, and yeah, unfortunately this is something very recent, so I don't have much more to say about it. Well, actually, yeah, I mean, in some very simple examples, like in the case of of G sets or continuous G actions, you get the usual space of orbits. But yeah, we don't know what happens in more general cases yet. What I would like to conclude with is to tell you about another two components that you can construct. Because, I mean, in that theory, there is also this notion of a setoid, which is like a groupoid, but you don't require the equations to hold. That may sound weird, but it works. And the point is that in the faithful case, you don't see the difference between setoids and groupoids. Okay? So in principle, there is no reason why this shouldn't work as well. But yeah, I mean, something of it works, but not in the same way, of course. So, for example, you don't get the monad, only an endofunctor here, and you still get a 2 comonad defined in the same way, but yeah, I wasn't able to show that it's outside potent. And so also the 2 monad in use is not going to be outside potent. And yeah, I don't know what the coalgebras and algebras are, but I have an example of a co-free coalgebra for this comonad of setoids, which is given in this paper. So it might be that this notion of maybe equality and quotient is too wild, or maybe it's more interesting. I don't know, but it's also there. Yeah, that's what I can say.
Thank you. We have time for one question, or maybe 2 short questions. Please, Steve.
I don't want to be the only one question.
So you mean the first one?
In the groupoid model of type theory, which I guess you're analyzing here, is this telling us that we can build quotients of groupoids in the model to get a groupoid quotient in the sense of hot?
I'm afraid not. I mean, the point is that the groupoid model is not an elementary calibration. So, so what is missing is that you don't have co-Cartesian lifts. I mean, you have lifts which are almost co-Cartesian, but the uniqueness part of the definition here doesn't hold. So you can construct, you can close the triangle upstairs, but not in a unique way.
What if you have truncation, zero truncation operation, and then you have existential operations on the groupoid model? In the sense of like a bracket type,
Yeah, that might way make it work. Yes, if you take the truncation of the equality, then yes.
And then I think you should also have the, well, but then maybe you don't have groupoid quotients, you only have quotients of,
Of propositional of equivalence relations. Yeah.
okay, that's close.
Yeah.
Thank you. Any more questions or comments? None, so it's time to thank you.